Okay, welcome to the first homework review video. We'll be going over some problems from Chapter 1, Homework 1, which is the first homework assignment of this semester. I'll be doing these every Monday after the homework is due, and be going over problems that, as a whole, people in the class had a little bit of trouble with, and try to shore up some of those concepts and go over some problem-solving strategies that I may not have had time to go over in class. On this first assignment, the performance was very good overall. 10.6 out of 12, so really nothing to worry about in terms of how you guys did as a whole. Another thing I should mention is that if you ever have problems that you want me to go over during one of these reviews, please let me know. I'll tend to do these on Monday, more likely in the morning than the afternoon, but sometime on Monday I'll be putting these together. So if you can ever let me know before Monday problems that you want me to cover or topics that you want me to cover, I'd be happy to include those. And then another thing I should mention before I start going through the problems that I'm going to cover today is that there were a couple problems on this homework assignment. They should not have been there. I thought I removed them, but I guess not. There are a couple problems that dealt with concepts related to the mole or Avogadro's number. So if you got one of these and did not get it correct, don't worry about that too much. That's a topic that will come a little bit later in the course. So I won't be covering those today because it's not a topic that we need to be familiar with at this point. But I will cover a few that we had some lower success rates on, and the first one deals with the Millikan oil drop experiment. So it says, in a Millikan oil drop experiment, the charges on several different oil drops were as follows: minus 5.92, minus 4.44, minus 2.98, minus 8.88. So the key concept here is in the oil drop experiment, he had an electric field and that was opposing some falling oil drops. So each oil drop could have some amount of charge on it, and that charge was caused by different numbers of electrons. So you could have 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on. But that means that the charge that was observed, that was measured by this experiment, was going to be some whole number multiple of the fundamental charge. So the idea here is, what you're looking for in this problem is, you're picking the answer choice that represents the fundamental charge of an electron, and all of the observed charges in the experiment, minus 5.92, minus 4.44, minus 2.96, and minus 8.88, those observed charges need to be whole number multiples of the fundamental charge. You cannot have a fraction of an electron. You can't have 1.1 electrons or 2.2 or 5.8. Whatever the case is, they have to be whole number multiples of the fundamental charge of an electron for this to work. So if we look at the answer choices, so the four charges that we're observing are minus 5.92, minus 4.44, minus 2.96, and minus 8.88. And so for each answer choice, we're going to figure out is the fundamental charge, is the observed charge some whole number multiple of the chosen fundamental charge. So for choice A, the fundamental charge is 1.11 or minus 1.11, since we're talking about electrons here. And I think this, and then if we look at the different possibilities, so this is going to be, so we're going to divide the observed charge by the fundamental charge. So you'd get a whole number 4 here, whole number 8 here, but the other ones are not whole numbers. So for example, 5.92 divided by 1.11 is 5.33. So the idea here is that if minus 1.11 is the fundamental charge, in order to observe a charge of minus 5.92, you would need 5.33 electrons, which is not physically possible. So choice A is out, because a couple of these are not whole number dividers. But if we look at choice B, and we divide all of these, 5.92 divided by 1.48, this charge would represent 4 electrons if the fundamental charge was minus 1.48. This one would be 3 electrons, this one would be 2 electrons, and this one would be 6. So we're just dividing the two charges. And so choice B looks like it could work because all of these numbers are whole number multiples of the fundamental charge minus 1.48. So we're going to pick B as our answer. We can check the rest of these and we can see also that they don't all work out. So this one would give 2.67 electrons for the 5.92, and then if we look at 2.96 as our fundamental charge, 4.44 divided by 2.96, you would need 1.5 electrons here. So we don't have to check every single one, but if any of these are not whole number multiples, then that answer can't work, and then choice E is clearly not going to work for any of them. So these are all invalid because they're not, the observed charges are not whole number multiples. The only one works is B. So this really just tested your understanding of the Millikan oil drop experiment, and the key concept is that when you have charged particles, they have to have some whole number multiple of the electronic charge, because you cannot have fractional electronic charges in any sort of particle or ion. Okay, so that one was a bit of a tricky one, and the rest of these are mostly just conceptual questions dealing with true, false, or which statement is correct, and all these things. Okay, so the next one is, which of the following statements is true? And so the first one, A, ions are formed by removing protons or electrons. So as I tried to emphasize in class, and this was an answer that many of you still selected, ions are only formed by adding or subtracting electrons. If you add or subtract protons, you're going to change the identity of the atom, so it's no longer an ion, it's something totally different, some totally different element that you formed. So when we're dealing with the formation of ions, which is something that we will deal with a lot in the beginning of the course, you're only going to be adding or subtracting electrons, nothing from the nucleus. Okay, so this one's false. B, scientists believe that solids are mostly open space. This one is true, and we know that from the Rutherford gold foil experiment. Okay, so remember that the Rutherford gold foil experiment showed us that most of the mass and all of the charge, or all the positive charge, is contained in a very concentrated, very dense region called the nucleus. So the vast majority of the mass, all the positive charge is there. And so that means even though electrons can occupy a large space, at any given time, most of the space in an atom is empty. So the nucleus takes up a very small space. Electrons themselves are very tiny. So there's a lot of empty space in atoms, and as such, a lot of empty space also in any matter that's made up of atoms, including solids, is choice B here. Okay, C, we didn't talk a lot in detail about the difference between physical and chemical changes, but here it says heating water with a Bunsen burner results in a 2-to-1 mixture of hydrogen and oxygen gases. If we're just heating water, we know what happens from our own daily life. We're going to start boiling the water, and boiling the water is not a chemical change. We're not breaking the bonds in water to make new substances, hydrogen and oxygen. So when you heat water in a Bunsen burner, this is just a physical change, not a chemical change. We're not going to be breaking any bonds or forming any new substances, so this one is also false. And then choice D and E are just at least 2 of these statements are true, or all the statements are false. Those don't work, so choice B is the only true statement. Scientists believe that solids are mostly open space. So that was how we want to think about that one. So 3 different concepts here, all in the same problem. The first one, A, deals with the formation of ions, which we should be aware is only involving electrons. Choice B, the idea that came from the Rutherford gold foil experiment, which is that most of atoms are empty space. Most of the mass is very concentrated, so you have a lot of empty space in atoms. And then choice C, which is the difference between physical and chemical changes, something we didn't touch on in class, but when you heat water, when you bring water to a boil, you're not going to be changing the composition of water, you're just going to be changing its physical state, and we will learn a lot more about physical changes later on in the course. Okay. The next question I want to go over is also conceptual in nature. It deals with the law of multiple proportions. So the first key thing we should look at, whenever we see law of multiple proportions, there's obviously more to it than this, but we should automatically think of 2 or more compounds formed from the same elements. So if you're talking about the properties of a single compound, that can't really be a demonstration of law of multiple proportions. In order to demonstrate the law of multiple proportions and all of its implications, we're dealing with 2 or more compounds formed from the same elements. Okay. So then we have a few choices here, and we want to decide which of these are represented by the law of multiple proportions. So A, if the same 2 elements form 2 different compounds, they do so in the same ratio. So this is kind of the opposite of what the law of multiple proportions says. The law of multiple proportions says if 2 elements form 2 different compounds, the 2 ratios are going to be different. So that's what makes them different compounds. If you have same elements, same mass ratio, that's the same compound. So in order to make two different compounds, you need to have different ratios of the elements. B, it is not possible for the same two elements to form more than one compound. Okay, this one is clearly false also. If this was true, we wouldn't even have the law of multiple proportions, but we know of many examples of this. So carbon monoxide and carbon dioxide, two different compounds formed from the same elements. We talked in class about two different compounds that form from iron and oxygen, and there's many other examples of this. We know of the whole class of molecules called carbohydrates, which are carbon, hydrogen, and oxygen. There's a whole bunch of different ones that can all form. So you can have many different compounds when you only have the same two elements that form. And again, they form in the elements combine in different ratios to form those different compounds. Choice C, the ratio of the masses of elements in a compound is always the same. This statement is true, but it does not deal with the law of multiple proportions. This one deals with the law of definite composition. So this is a true statement, but remember, if we're talking about multiple proportions, we're talking about two or more compounds formed from the same elements. And the law of definite composition just says the composition of a specific compound will always have the same ratio of elements. Okay, so that's a true statement, but not dealing with multiple proportions. And then finally, choice D, the total mass after a chemical change is the same as before the change. This is also true, but it's a different mass law. This is the law of conservation of mass. Alright, so as it turns out, none of these answer choices deal directly with the law of multiple proportions. So the correct answer here would be E, none of these. And I know sometimes it's a little bit disconcerting to put none of these as your answer. You always assume that one of the answers is right, but in this case that wasn't the situation. Alright, so the last one I want to go over here now is sort of an atom level view of these mass laws. And so we have over here on the left we have a series of atoms. They're all just single atoms of an element, and they're combining to form some compounds with some individual atoms left over. So we want to see which of the mass laws are demonstrated by the figures below. Alright, so if we want to look at choice A, law of conservation of mass, in order to demonstrate this law, we need to have the same number of particles, the same kinds of particles on the left and the right side, because the law of conservation of mass says matter is neither created nor destroyed in a chemical reaction, and that the identity of the atoms don't change. So if we look at this starting point here where everything's an individual atom, we count the different ones. We have, if I can count correctly, we have 7 purple, and we have 9 green. Sure hope I counted those right. So that's what we're starting with, 7 purple atoms, 9 green atoms, whatever those represent. And then what we're ending with after the chemical transformation, if we count the purple atoms, we have 1, 2, 3, 4, 5, 6, 7 purple. And if we count green, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 green. Okay, so we have the same exact matter or mass before and after, so the law of conservation of mass is demonstrated by this picture. So law of definite composition, this one will be demonstrated if the compounds that form have a definite ratio of atoms or elements that form them. So if we look at the molecules that are formed, which are the ones that are going to have multiple ones, we have each molecule is going to have 2 green and 1 purple. So the compound that forms over here on the product side has a definite composition of 2 to 1, green to purple. So law of definite composition is demonstrated. Law of multiple proportions, remember that in order for this to be demonstrated, we need to have 2 different compounds formed from the same elements. And if we look at the compounds that are formed over here on the product side, we only have one kind. We have everything has 2 green and 1 purple. 2 to 1, 2 to 1, 2 to 1, 2 to 1. So there's only one compound formed from these 2 elements in this particular reaction. So the law of multiple proportions is not demonstrated or illustrated by this figure below. Okay, so that one's out, and then the rest of these are just combinations of the 3 answer choices. So looks like the one that's going to work out is choice D. Conservation of mass and definite composition are demonstrated by this reaction, but we do not demonstrate law of multiple proportions because in this case we only form one compound, and law of multiple proportions deals with forming 2 compounds from the same set of elements. Alright, so hopefully those are clear. If you have any more questions on these, I encourage you to ask me in some way, either by sending me an email or coming to my office, and I will see you back next week with our next homework review.